All right, we'll start right now. Good afternoon, CS 186. Professor Hellerstein is going to be a little late today, so I'm going to start off what we're covering today, and he'll come in partway through the lecture and continue off from where I left off. So, if you came to that last lecture before the midterm, I know a substantial number of people were home studying. But if you came to that lecture, we talked about functional dependencies and schema refinement. And this is a part in this class where we talk about basically we bridge the logical design of our database with the physical design of their database. So given our logical design, how do we turn our entity relationship models into schemas, which we can then put into our database as tables or relations, and how to design these schemas properly so that we can be as efficient as possible when we're representing our data and when we're keeping our data up to date. So before I go into the details of what we're going to talk about, I'd just like to say that this is really useful, really useful if you're ever going to get a job in software engineering. And a cool class to be taking is CS 169, which I believe is the software engineering class. But in that class, you're going to learn about exactly a lot of things that are happening today, which most technology firms are doing with respect to designing web applications or other kinds of applications. And what a lot of these applications have to do is they have to manage lots of data. They need to be able to organize their data, lay it out somewhere on disk or maybe over the network in the cloud, and be able to effectively query this data when necessary for the application. So last summer I worked an internship at this small, obscure company. You may have heard of them. I interned at IBM, and to be specific, in the Big Fix division up in Emeryville, which is pretty close to here. But one of my projects was to make this application that, so the product that I worked, the division I worked in made this product that described this distributed IT management system. So if you're a company like Walmart, you have a ton of computers, and these computers may be running Windows or Linux or other operating systems. And one of the things that this system did was that it delivered patches to customers. So we wanted to keep these patches up to date. If there's some security flaw in this system, we want to be able to deliver it. And so the project was this. There was this typical web application front end, but behind that front end was this database, 200 gigabyte database, lots of data for every platform that's ever existed or that the company is keeping track of. We want to be able to search this data. We want to be able to update this data when new patches come up, etc. And so how do we do fast searches? Well, indices, right? We talked about indexes in class earlier. In fact, it was on your midterm. It turns out indices are really effective in real life, and it'll help you perform queries on your database a lot faster. Another issue that I ran into was handling bad input, or maybe during an update, maybe there's a power outage, and you're in the middle of some update, and everything crashes. What do you do? Well, we'll talk about this later in class, but it turns out that the error recovery and transaction mechanism, the transaction abstraction that databases support, are really useful, and we're going to cover this later in class. But the fundamental issue right now is how do we design this database in the first place, right? When we have our web application front end, and we're querying this database, how do we want to organize our data so that all this happens efficiently and we're not tripping over the kinds of abstractions that we picked in the first place during the design of the database. And some neat side note, all this was done on a tiny computer and just with SQLite, which is not exactly the best database management system, but leveraging these principles can help you, make much more efficient kinds of front ends for these for data. So the stuff that we're talking about in these few lectures are really important. They'll help you actually use the concepts of databases in real life. You may never design an index data structure or some kind of algorithm to handle error recovery, but you will probably, or you will definitely, if you work in software engineering, deal with the design of data in the first place. Lots and lots of data. Okay, so let's get into the material. So one of the issues when we're designing a database is that we want to avoid redundancy. Not redundancy in redundancy in the sense that we're keeping copies of data where we shouldn't be keeping copies of data, right? And first of all, this leads to wasted storage, which is always a problem. But it's not really a big problem, right? Disk space is cheap. You can always buy more disks. The more important problem is the anomalies that are introduced when we have a lot of redundancy in our database. And last time we covered insert, delete, and update anomalies. All different classes of anomalies that you'll run into if you realize that if it turns out that the design of your database isn't exactly appropriate for your problem. So the solution that we're trying to our proposed solution to this problem is functional dependencies. And functional dependencies are a way of formalizing these kinds of integrity constraints which kind of describe the relationships of different columns to each other, right? Different fields in our relations. And what these functional dependencies help us do is they help us identify redundancy. They help us identify redundancy in how we're storing our data and help us refine the design of this data. And the main technique we're going to be covering in this class is decomposition. When we have some sets of tables, when we have some table, how are we going to split? How can we use decomposition to split this table into smaller tables? Smaller tables which reduce the amount of redundancy that we're keeping around in our database. And decomposition is really useful, but we also have to be careful that we do this judiciously. As in, we want to make sure that our functional dependencies are able to be preserved, and we'll go over this later today as we refine our database. So let's go over some anomalies. Consider a table. So we went over this example last time, but consider a table with employees, their ratings, and their pay. And we're going to say that an employee's rating determines his or her pay, right? So if an employee's rating determines his or her pay, and we have this table with all three of these columns, then you can imagine a case in which updating this table introduces some kind of anomaly. And there are three kinds of updates we can do to a table. We can update a row, as in we can change the value of some column in a row. We can insert a row into our table, or we can delete a row or we can delete rows from our table. And these different kinds of updates can potentially introduce different anomalies. So, for example, if we have a bunch of so I'll go draw an example up here. So if we have a table whose columns are employee ID, rating, and pay, and we're going to have some employee IDs and some ratings. And the pay that's associated with that rating, maybe like an hourly wage or something. So, So we can imagine that performing updates to this table would introduce some kind of anomaly into this table. So if we, for example, for employee with the ID 1, if we changed that employee's pay from 15 to, say, 20, then now we have an update anomaly. Because if we say that an employee's rating exclusively determines his or her pay, and we do this update, we now have two employees with the same rating and different pay. Any questions about what an update anomaly is? Okay. Furthermore, we can also insert entries in this table which may not be determinable by the information that we have in this table. So if we insert an employee with a rating of 7, how much should she or he be paid? We don't know that because that information isn't encoded properly in our table. And finally, if we delete an employee with a given rating, if we say delete employee with the ID 3, that will destroy some information. That will destroy the information of how much pay an employee with rating 5 should receive. Right. So our solution to this problem is decomposition. And essentially we decompose this table into two different tables, naturally. Instead of keeping pay in the same table, we'll construct a new table that maps ratings to pay. And now we'll put our new information, our new pay information into this table. Okay. Are there any questions about anomalies? Okay. Cool. So functional dependencies. So a functional dependency is functional dependencies are the kind of functional dependencies are the formalism we'll be using to basically attack this problem of redundancy. So we're going to have this formal definition of a functional dependency between two columns in a relation. So the idea is that so we have two columns x and y in a relation. We can define a functional dependency between x and y, saying that x determines y if for every allowable instance of our relation, for any tuple in that relation, if we have two of the same values for a column for x in two tuples, then they're going to have the same value for y. So to illustrate that, let's say we're given a relation of x and y, and we're given this relation, and if we have two tuples with the same x value, 3, and they have different y values, then this functional dependency does not hold. We can have one value for x determine two different values for y. So functional dependencies are intimately related to keys. In fact, keys are just one specific kind of functional dependency. If we have a relation and our key, our set of columns determines the whole relation, then we'll say that that functional dependency is actually a key. They're basically the same thing. Keys are just one specific type of functional dependency. And we'll introduce some definitions. A functional dependency G is implied by a set of functional dependencies F if G holds whenever all of the functional dependencies in F hold. So F is a set of functional dependencies that describes several dependencies between from some set of columns, and we'll say that if we can get from one functional dependency in F to G, then we'll say that G is implied by F. And we also define the closure. It's a closure of some set of functional dependencies F is all of the functional dependencies that we can get from F. So we have so the axioms that we're going to create this system that allows us to get from one functional dependency to another, and we're going to do that using Armstrong's axioms. And this is a set of 3 axioms: reflexivity, augmentation, and transitivity, such that if we start out with some functional dependency, we can use one of these 3 rules to get to another functional dependency. And in fact, these rules are sound and complete. If we want to find the closure of some set of functional dependencies F, we can just use these axioms to get from F to our closure. And so we have from Armstrong's axioms, you can actually derive the rules of union and decomposition. Union, where you can take 2 functional dependencies from one column and combine them, and decomposition, where you can do the reverse. Okay.
I got to say, it's hard enough to stand up in front of hundreds of people and YouTube and give a lecture when, you weren't given a lot of heads up that you're going to do it. But to do it in front of the guy who teaches the class is really frustrating. So I hope... anyway, I want to thank Derek. He did a great job. That was awesome. And I will say, for all of you, public speaking is a super important skill for engineers to have and for leaders to have. And if you want to be a leader and an engineer, even better. I encourage you guys to take opportunities to get in front of folks and speak. Really good thing to do. There's while I'm getting set up here, I'll just riff on this a little bit. There's an meetup called Papers We Love that runs in San Francisco and Oakland, mostly in San Francisco, where people come in and talk about a paper, usually not their paper, but a research paper that they love. And they're also webcasted. You can go watch them on the web, but they're great. So a bunch of my former students go regularly and have presented. There tend to be more experienced engineers who do them, who remember fondly their days in master's programs and things like that. But still, I think you guys would enjoy it. So you can look at that on the web. And after attending a few, maybe you'll be inspired to run one. The other thing I'll say is that I've had students over the years who've been uncomfortable with public speaking, and some of them have done Toastmasters, and it's been great. It's been super, super helpful to a bunch of students I've worked with over time. Sorry, this was the last thing I was doing. I've never been, but I'm impressed with people's what they've gotten out of it. So there's Toastmasters groups in Berkeley. Really, really important skill. All right, I have to bring up the right lecture. It's been a while since we had a lecture, huh? You guys had a little exam along the way. There we go. All right, Derek, that was awesome reminder of where we are and the basics, because what we've been doing since then is driving all that functional dependency knowledge and decomposition intuition into coming up with normal forms that will give us some nice guarantees. And what I'm going to do is jump right into the normal form that makes the most sense, which is Boyce-Codd normal form. And yes, excellent. With a little help from the projector, we can get going. So exactly this decomposition that we just did, that Derek just went through, where we took something and we put aside a functional dependency rating to pay in its own table, where now this table has a key, right? And there's a foreign key here, but there's no longer a R to P functional dependency left in this table. That's the decomposition we sort of feel like we want. If we've done this decomposition over and over, and we get down to tables that only look like this, where they only have key dependencies, then in some sense we've just got tables that have the basics. Each table individually has no redundancy in it, right? And somehow we've captured everything we want. And that is the essence of Boyce-Codd normal form, and it's also the intuition for how we take a schema and drive it to Boyce-Codd normal form. So kind of repeatedly applying this intuition pretty much leads you to BCNF. But let's define it carefully so that we can talk about actually what it really gives us. So this is review from last time, but it's worth doing. A relation R with functional dependencies F is in Boyce-Codd normal form if for all x determines A and F plus. if for any functional dependency we could possibly derive from F, right? That's what F plus is. Anything we could derive from F via Armstrong's axioms. If for all of those, which is exponentially big, don't forget, so this is hard to test. All right, we're going to have to prove it without enumerating, right? For all of those, if it's the case that either the FD is trivial or the left-hand side is a superkey, meaning it determines all the other columns, then we're good. Then we're in Boyce-Codd normal form. Another way to say this is R is in BCNF if the only non-trivial functional dependencies are key constraints. Wouldn't it be a nice world if the only FDs we had were key constraints, because then there'd be no redundancy. Everything on the right-hand side of a functional dependency could only appear once, because the thing on the left-hand side can only appear once because it's a key, right? If you're a key column, you can't have duplicates, right? So look at the ratings table. 2 can only appear once, so this mapping of 2 to 15 only appears once. That's the world we want to live in. So another way to think about it is everything we write down in that environment is necessary information. Nothing can be derived from some combination of other tuples and FDs, right? So here, look at this example. Suppose we know x determines A, and we have this table, little x with little a. So then little x here should also be with little a. And writing it down again is redundant. If we can fill in the blank via a combination of some other tuple and an FD, then the thing is not in Boyce-Codd normal form. Right? And there's some sort of connection here to compression, right? Somehow BCNF has got the functional dependency notion of compression captured. We've only written down the information we need to construct anything. So how do we do it? How do we compose any arbitrary relation or set of relations into Boyce-Codd normal form? And the answer is we do pretty much what Derek just went through. We're going to decompose out these FDs into separate tables. So suppose R contains attributes A1 through AN. Let's first define carefully what a decomposition is. A decomposition of R consists of replacing R by 2 or more relations, such that each new relation scheme, that is to say the schema of the relation, contains a subset of the attributes of R. All right, so we're not going to manufacture any new columns, first off. Second, every attribute of R appears as an attribute of at least one of the new relations. Every attribute somewhere, okay? So we took all the attributes that were in R, we created a new schema. It's got to have no new columns, and it can't be missing any of the columns from R either, okay? That's pretty straightforward. If you've done that, that counts as a decomposition. Right, so decomposition is very loose here in this sense. You just can't construct or lose column names. So here's an example. So this is the same example as we've been having. This is this Miller example where S is a key and rating determines wage. Right? R determines W. Is it in BCNF? We know the answer to that is no, because of rating determines wage. This is the example we've been going through over and over. The wage values are repeatedly associated with the rating values, right? We see 810, 810, 57, 57. They're repeated, right? So it's not in BCNF, right? Because it violates the rule it violates the second rule. X is not always a superkey. The left-hand sides of the FDs are not superkeys. R is not a superkey. Okay. So how do we decompose the relation? The easiest fix is just to create this relation RW and remove W, the dependent attributes, from the main schema. So like we did before, we'll just put ratings wage lookup table off to the side. Right? Now, recursively, we have to ask the question, is each of these relations in BCNF? Well, on the left-hand side, the only functional dependency left from F that still applies is S determines NLRH, right? That's non-trivial. And through transitivity, there's no other closure of those FDs. So actually, it's pretty clear that the only interesting functional dependency here is F determines NLRH. That has S on the left-hand side. S is a key, so it is in BCNF. All the non-trivial things over here that you could possibly derive in F+, have a key on the left-hand side of the functional dependency. What about over here? We started, remember, with F. F was S determines everything. And we also had R determines W. Clearly, nothing you can, these guys don't generate a whole lot more dependent functional dependencies via Armstrong's axiom. So it's easy to figure out what F+ is if you ignore the trivial dependencies. Okay. Is there anything over on the right-hand side there besides R determines W? Does W determine R, for example? No. Okay. So there's only non-trivial dependency on the right-hand side is R determines W. R is a superkey of this table, right, by construction, because R determines R and R determines W, so R determines RW. We built this table so that would be true. So this thing is in BCNF. All of its FDs on the right-hand side are either trivial or have a superkey on the left-hand side. So what we did is we took a table that was not in BCNF, and we constructed two tables that are in BCNF, and that makes us happy. Because now we've written down the minimal amount of information. We will have no anomalies on update. Now, we don't want to decompose things too far. We could keep decomposing the thing on the left just for fun. We don't need to because it's already in BCNF, but we could. Why wouldn't we just kind of keep breaking it down into 2 columns or 3 columns pieces? What might be bad about that if we did that? Yeah, putting them back together might be the thing you spend all your time doing, right? If you ask queries on SN, L, R, and H a lot, then you're going to have to join up the pieces back together every time you ask one of those queries. It's much nicer to scan a table than join it. Okay, that's a good argument. Can anyone think of any other problems that you could have with decompositions? Yeah?
Wasting storage on the primary.
Excellent. Okay, so if we break this thing up on the left into, say, SN and SLRH, okay, well, they both have the right key, which is S, but S is now being repeated. Seems like a shame. So that's a really good point. Maybe we shouldn't do it that way. Maybe we should do a different decomposition. Maybe we should just do SN and LRH. Is that going to be cool? That's not going to be cool, but we're not exactly sure. Why is that not cool? It's a decomposition. We've covered all of SN, L, R, and H somewhere. We have added no new columns, so it is a legal decomposition. Why might it be bad? Yeah. Yeah, how the heck are we going to join these guys back together, right? That's a problem, okay? So we're going to have a formalization for this. This is we've lost information is a way to look at this. We tore some stuff apart, and we can never put it back together. We lost the way that it was connected. The fabric of the universe was rift. There's a rift in the fabric of the universe. All right, what else might be bad about this? Maybe nothing. Maybe that's the main bad thing here. There's another bad thing we'll see, but I can't get it out of this example, so let's go through it. Here's some problems with decompositions. There's roughly 3 of them. Actually, let me ask a question. What might be good, for a moment, about doing this? So we can always join it all back together by S. Is there a good thing maybe there? What could be good about that? Yeah. Caching. Why would that be good for caching? Interesting.
If you aren't only concerned, or you're doing multiple operations on only the name and the ID, then you can just load that table into the cache and crank through your operation.
Great. It's not only true for just caching, it's true for disk bandwidth and many other things, right? So the point that was made, to repeat it for those of you who didn't hear and for the posterity, is this might be good for performance issues like caching. Suppose you often look only at S and N. Well, then why are you dragging all this other stuff into memory where it pollutes the buffer pool and you get poorer cache performance? That was the example. Also, to scan SNLRH takes longer than to scan just SN because SN has fewer bytes on disk, right? So this is sometimes called vertical partitioning, and it's a trick for making certain query workloads go faster. All right? You do this not because of any kind of redundancy thing. You do it for physical performance. All right? It is a decomposition. You're taking the table and you're slicing it vertically, so to speak, in order to get faster IOs, less cache pollution, and all that good stuff. All right? And if you take this to the limit, you build a system that's designed exactly around this, and you get what's called a column store. So you may have heard of column store databases. They're just databases that aggressively vertically partition everything under the covers. So even though you said your table has 5 columns, under the covers it tears it up into little columns, and then it puts the columns back together under the covers for you. And that can have really great performance implications if you tend to query subsets of the data, right? Subvertical, subsets of the columns. It can be expensive. It can be a lose. These guys often lose if you find yourself joining stuff back together a lot. Okay, so it's sort of, they're just making that trade-off for you under the covers. In SQL, you can make some of the same trade-offs yourself just by partitioning. But remember, you need this S here to join it back together. The column stores will often find a way to join it back together without S, like by keeping them ordered in a particular way and joining them by position. Row number 1 is going to be row number 1 in all of the partitions. So they can guarantee that when they implement it. The relational model does not guarantee you that this will be stored in the same order as that, right? And in a traditional database, if you partition like this, they may indeed deliver these in different orders. All right, but in a column store, they'll just make sure to store these in the same way and deliver them in the same way and join them then by row number in a merge join. All right, I'm getting kind of ahead of myself. If you didn't follow any of that, that's fine. But if you hear about columnar databases or column stores, it's really this intuition that you had, that you can get some performance out of separating attributes that don't get queried together into separate tables.
So you're saying it would be pretty straightforward for the column store to put all those tables on the same page?
Oh, I didn't say that. The question was, would it be straightforward for a column store to put all these tables on the same page?
Wouldn't that make a huge difference with like joining access?
Yeah. So you start to get into some implementation specifics about things like where on the disk do these different attributes live, and if they're stored sort of intermingled, how might you do that? And even what would your page layout be if you wanted to super duper optimize this? It gets even lower level than that. How would you want to encode the values? Because if you've got a column that's all integers, because it's the L column, maybe you encode them using like Huffman codes because they compress really well, because they're all integers now. They're not tuples. So lots of tricks all the way down, and I don't want to derail class on this, but they all follow from this idea of vertical partitioning. All right, and under the covers, you can play all kinds of fun games. Okay, the vertical partitioning thing, though, you can do even in an SQL database. So let me re-emphasize that. Outside the box, as long as you keep a join key around, like S, right, you can do this and you can get some of those performance benefits in the cases where that's valuable. Okay. That said, I'm now going to warn you for the rest of the lecture about when it's bad to decompose things because it gives you badness. All right, and the badness will be semantic badness, not performance badness. All right, you're going to lose information, for example. All right, so what problems might we get from decompositions? Now that we've seen there may be something good about them sometimes for performance. There can certainly be bad things from performance. Okay, so here's the worst problem, though, which is the one that was mentioned. It may be impossible to reconstruct the original relation. So I erased it. Let me put it back. We had Sniller H, and we decomposed it into SNL and say RH. All right? It's not at all clear. In fact, it's pretty much impossible to join these back together. They don't have any common attributes. The best you could do is cross-product them back together. How many rows would the cross-product of this thing have? It would have the square of the number of rows that the real table has, right? Because if the real table has n rows, this has n rows, and this has n rows, and if you form their cross product, it's got n squared rows. So you got n squared minus n weird rows in that table that never belonged, okay? There's no way to put it back together. So that's called lossiness. We've lost information. We've lost the information about which of these couplings is real and which of them are not. Now, we didn't get that when we took rating and pay out of this employee rating pay table, and we didn't get it when we took out rating and wage out of Snillerwe, because rating was a key, actually, for wage, and we kept it around here, so we could join on R. All right? So we'll talk about this in more detail in a minute. So this was not a problem in the example we saw in the previous slides, and we'll see why. Second problem, we haven't talked about this one yet because I didn't have a good example on the board. You may have dependencies in F+ that now have the left-hand side in one table and the right-hand side in another table, which means if you're implementing under the covers dependency detection, which the database will do for you, every time somebody does an insert in one of those tables, you have to do a join to see if it's going to be a problem for that insert to happen. Because you've got to go check the dependency, and the columns are in two different tables. So that could be actually expensive. It's not going to be wrong, but you'll be turning inserts into joins. Inserts are supposed to be little writes, like one write to one page, and suddenly now they're joins. That's bad. Okay. And then the last one is some queries become more expensive because you got to do joins you didn't need to do before to answer the queries. And you do want to be sensitive to your workload. What kinds of queries do you tend to get? and design your workload design your layout to fit your workload, right? So it's a concern. So you have to trade off sometimes these concerns against your desire to get rid of redundancy. We're not going to trade off number one, okay? We're not going to turn our data into wrong data. But we might trade off 2 and 3. We might trade off performance of queries against managing redundancy of inputs. All right, let's look at this concrete example again. Remember, Sniller got turned into Sniller and RW, but we join them back together on R. We don't get n squared rows, we get n rows. And in fact, we get the original n rows, thank goodness. This seems to work. Now, precisely why did it work? Maybe let's look at some examples where it doesn't work. We had one example on the board where it clearly didn't work, but let's look at this one. Very interesting data on these exciting columns A, B, and C. And we know that A determines B, and actually C determines B. Let's decompose that, because we have some functional dependencies. Let's pull out that CB pair into its own table. So C determines B, so we'll have a table just for C and B. Okay? We decompose like that. We have B in both tables. If we put it back together, do we get the right answer? If we join on B, do we get the same table we started with? We don't, right? Because look, at the B column originally had 2 2s in it. When we join these two guys together, how many 2 pairings will there be? 4, right? Somehow there's a cross-producty thing happening that shouldn't have happened. It's kind of the example of that full cross product n squared I said in the small, and just the value 2. It's a value by value cross product. These values are duplicated. Because 2 is duplicated, instead of getting 2 of them, we get 4 of them. It equals that. And we got 2 spurious rows out of this, right? Because instead of 2, we had 4 copies of the number 2 in the B column, right? That extra 2's led to 1 in the A column being associated with 8 in the C column, right? Because that first row of AB joins with that last row of BC, which it shouldn't have. All right, so it's not as simple as just making sure that both tables share a column. Something has to be true about the columns they share. And we want to guess what we have to guarantee about those columns? It's a little subtle, yeah? Bijective, not quite. So that's really strong. Bijective would be it's a key in both directions. And it's not clear which bijection you mean.
So each C corresponds to one B, each B, and each B corresponds to each C.
Good. That would work. It's not required, but that would work. So if each B corresponded to one C, and each C corresponded to one B, if the BC table had keys in both directions, it was bijective, that would certainly work. So that's good. It's sound, but it's not complete or something. It's a little conservative. There's other cases that'll work too. Yeah?
Each B corresponds to one A and each B corresponds to one C.
That would work too. So if each B corresponded to exactly one A and each B corresponded to exactly one C, when we put them back together, we'd be good. That would work. Also too conservative, though. We can be even more flexible. Yeah? Each AB corresponds to one C. How would that come about? That would definitely work. That's a nice characterization. What function? So you could say AB determines C, but they're in 2 different tables. So what would we need to make that idea fly? If each AB determines a C, yeah?
The entries of the common column has to be unique.
Oh, excellent. The entries of the common column have to be unique. The common column is B. Yeah. If B is unique, what can we say about the BC table? B determines C, because B is a key. If B is unique, it's a key. So the thing on the right, B would determine C, and that would do the trick. Great. Now this example is a little funny because we just have these 2 little tables on each side. But the general idea you had is the right one now. After some refinement, we relaxed our requirements, and we got to the thing that we're looking for. So we'll say that a decomposition of R into subsets of columns X and Y is lossless join with respect to the functional dependencies we have, F. If for every instance R that satisfies F, so every table with real data in it, little r, that satisfies F, do the decomposition, which is to say project R down to the X attributes, project R down to the Y attributes, join them back together, you get the original. This is just saying you can put it back together. Okay? We say it's lossless join if you can put it back together. That's all that notation said. When is that true? It's always true. Well, before we say when is that true, note that the thing you get when you join it back together is either the original thing or something bigger, right? Something with spurious combinations. It's never smaller, right? It's always a superset of R. But it's bad to have a superset, right? You might think, well, that's cool, so we generate some extra stuff. We never lose any information, but you totally lose information because knowing that something is not true is information, right? Knowing that Bob doesn't work in the shoe department, he works in the toy department, is information. If suddenly you also know that Bob works in the shoe department, that's wrongness, and you've what is wrongness? It's the absence of rightness, right? But it is always true you make something bigger. It's just maybe full of junk. All right. In general, the other direction doesn't hold, right? So if you do put them back together, you may not get something the same size. If it does, the decomposition is lossless join. And you can extend this definition in a straightforward way to 3 or more relations. We must ensure that things are lossless join. How do we guarantee it? Which is what we were figuring out on the fly. The decomposition of R into X and Y is lossless with respect to F if and only if, so this is exactly what we want, it's neither too restrictive nor too loose, if and only if the closure of F tells us, so F plus tells us that the overlapping columns, exactly the way you described it, the overlapping columns of X determine Y determine either X or Y. So it's a key on one side of the decomposition or the other. It doesn't have to be a key on both, because think about it. Suppose we have a relation with lots of tuples, and we carve off these 2 columns, call them R and W, since that's familiar, and we put them over here. This is probably smaller than that, right? Ratings and wages was smaller than employees. But R is a key of this one. It's not a key of this one. We wouldn't want it to be a key of this one, because then we could only store 1 employee with each rating, right? That'd be no good. But it is a key over here, and when you join them back together, for every one of these guys, you get exactly 1 match here. And that means you get the same sized output as you get input. This thing, for every row of this, there's exactly 1 match, so the output's exactly as big as this one. The other way around, it's the same argument. It's just the question of who's left and who's right. Okay? So it just needs to be, the overlapping columns need to be a superkey of one of the decomposed relations. And how do we know something's a superkey? We know it from F. That's why this whole thing is defined in terms of F and F+. Make sense? None of this makes sense without functional dependencies. We can't even think about how to do this without functional dependencies, which is why they're so awesome. They're kind of awesome. They're a little awesome. It's here for functional dependencies. All right, so here's an example that works. If we decompose on C, well, guess what? C determines B. So we're good, because C is a key of the right-hand side. When we join it back together, for every tuple in AC, there's exactly 1 match in BC. Okay? C is not necessarily a key of AC, by the way, although in this example you can't tell that. But from the FDs, A determines B, C determines, From the FDs, C is not necessarily a key of the left-hand side. In fact, it's not. Okay. Here's the thing. If I have A determines B, which I do, the only way to check it when someone inserts a new B is to join things back together on C and make sure they're not violating this functional dependency. How do we avoid redundancy? By doing a join. That's a drag. Every time somebody does an insertion on one of these 2, we have to do a join to check for redundancy. So that's a bummer. So this is the second problem, which is called a dependency-preserving decomposition. So just to review, and let's pause, what we studied up to now is lossless join decompositions. You must have your decompositions be lossless join, or you will generate spurious information. Everything we're going to talk about next is about performance. Okay, so this is like, don't screw this up. Right? The rest of the stuff, it'll just make you go slow. All right. Dependency-preserving decompositions. The slides get kind of thick towards the end of the semester, so. All right. A dependency-preserving decomposition is one that doesn't make us do joins to check dependencies. But it's tricky because we got to think about the closure of F, not just F. So let's figure this out. Dependency-preserving decomposition, here's the intuition. It's one where the following's true. If you take R, decompose it into, X, Y, and Z. 3 different subsets. And let's enforce the FDs locally on X. And we'll enforce the FDs locally on Y. And we'll enforce the FDs locally on Z. Our goal is that that's good enough, that we never have to enforce dependencies on anything that's joined together. So what we want is we want that enforcement locally, table by table, to achieve the same effect as if it had all been joined together and we were enforcing F on the full table. That's what we want. Okay. Now we can be really formal about that, but first we're going to have some notation. Okay. But that's the intuition, so we'll start with the intuition. Everybody get it? You're going to break it into 3. I want to enforce functional dependencies on each one individually, and I want to get the effect of enforcing the functional dependencies on the whole table, original table. All right, how do we talk about this carefully? First, we have to talk about a projection of the FDs. We know what a projection of a table is. Now we have to talk about what does it mean to enforce F on only this subset of columns. What does that mean? So let's be careful about that. We're going to define a projection of a set of FDs. If you take R, you decompose it into just 2 for now, X and Y. The projection of F on X, which will denote F sub X, is the set of FDs U determines V in F plus, such that all of the attributes UV are in X. Okay? It's what you think it is. Take all of F plus. It's the things that are relevant to this table. They talk only about columns of this table. But we need to do F plus, unfortunately, because lots of things can be broken down into smaller FDs than the ones we wrote down in F, and then start to apply to projections. Okay. Now, what we're going to say, now this is formalizing what we said in intuition before. The decomposition of R into X and Y is dependency preserving if F sub X, the projection of the functional dependencies to X, union, the projection of the functional dependencies to Y, equals the application of F to X union Y, right? Equals F plus. That's a dependency preserving decomposition, right? This was just a careful way of what we said, saying what we said before. And it pointed out to us that there's an F plus floating around, which should make us nervous because that's exponential. And it is important. All right. Oh, gosh. I put a hard thing on the slides. I have A, B, and C as my original table. I have A determines B, B determines C, C determines A. It's decomposed into A, B, and B, C. All right, so I took A, B, C. I split it into A, B, and B, C. Let me write it down. This was my original set of columns, and I split it into 2 different tables, AB and BC. So I've replaced this relation with these 2 relations, and I have A determines B, B determines C, C determines A. Sort of weird cycle of functional dependencies. It's a weird example, don't get me wrong. It's a little artificial. But my question is, down here, is the C determines A functional dependency preserved? If I just take these 3 functional dependencies, I form their closure, and I apply the projections, and I enforce these things here and these things here, is it preserved? Well, let's be sloppy. Let's just look at F. Let's forget about F plus for a sec. Let's just see if maybe it's good enough to do it with F. We know A determines B is enforced here. That's cool. We know B determines C is enforced here. That's cool. Okay. Is C determines A kind of being taken care of for us? Can you put in a C with 2 different A's if I enforce these 2 things? Could I put in the moral, so here's ABC. C is supposed to determine A, right? So I've got 1, 2, 4. Could I have 4 here with a different A? Could I insert that with some value of B? What value of B would it be? Question mark. That's a question mark. Like the Riddler. Somebody said 2? Let's try to put a 2 in on B. See if that works. All right. Well, B determines C, so that's good. Because we preserved that. That would have been enforced here, so that's good. What about over here? Are we okay? A determines B? We didn't break anything with that. So far, it looks like we're not doing a very good job. Looks like this is not dependency preserving. But we were only looking at F, after all. We weren't looking at F plus. Let's be more careful. What about F plus? What's in F plus that's missing from the board right now? A determines C, which is not going to be in any projection. It's neither going to be here nor there. But F plus also equals the following. A determines C. What else? Transitivity is our friend. It's a cycle. If you have a cycle, what determines what? Everything determines everything. Okay. So we have in also B determines A. So sorry, I should have said A determines C. B determines A. C determines B. All right, C determines A. Did we get everybody now? 4 plus 2 equals 6. I think that probably is right. Is that right? Are we missing anything? All right. Sorry? B determines A because B determines C and C determines A. By transitivity, B determines A. Crazy, right? So now if we take the projection of this thing to AB, we have to add some stuff. We also have this enforced here, and we also have this enforced here. And now let's go back and ask our question. We wanted to put, question mark, not 2, question mark, what can we put there? So our first guess was we could put 2 there. Can we put 2 there? Question mark. Why not? Because B determines A, and 2 then must be paired with 1. But you've said that 2 is paired with 3, so that's no good. So it can't be 2. So it can't be something that's already in the B column because it'll screw up that direction, right? Unless you can find something that's already associated with the 3. So it can't be 2. It must be something that we haven't seen before. Right? Generally speaking, anything we can put in here, it's going to work. So yes, the short answer to this, and you can stare at it for a while, is this is dependency preserving because of F plus, not because of F. All right. So I'm going to put this question mark back here. It's a tiny little example. But the news is good. You can work on it at home. This is dependency preserving. You can't put something in there that wouldn't have been legal in the original ABC. How do we test for this? All right. Well, we know the definition. Boy. Yeah. I think that's the answer to what we just did on the board. That's not very exciting. It was more fun to do it on the board. So what we're going to do is we're not going to test for dependency-preserving decompositions on a case-by-case basis. What we're going to do is the decomposition we like that gets us into BCNF. And we're going to, someone is, not us probably, but someone has proven that decomposition, where we take out FDs and we put them into a separate table, that is dependency. No, it's not. We'll go through this. No, it's not. All right, let's talk this through. Let's just leave that on the table from before. We want to avoid things being not dependency preserving if we can. So let's see if we can decompose things into BCNF and get everything we want. Lossless join, dependency preserving, awesomeness. Let's see. All right, consider a relation R with functional dependencies F. Let's convert it into BCNF. If it's already in BCNF, we're done. That's fun. So let's assume it's not in BCNF, and it has some particular FD in there. X determines Y. That's the culprit for now. That's one where X is not a superkey, and Y is not a subset of X, so it's not trivial. Right? It's a non-trivial FD, and X is not a superkey, so it violates BCNF. So we're going to decompose it just like we did over here, just like Derek did, into R minus Y and XY. Right? And we'll be able to join it back together on X. Agreed? There's ratings and wages all over again. If you do this over and over, we will decompose things into BCNF. Theorem, it will be a lossless join decomposition, or really rather assertion, because it takes almost no proof whatsoever. This will be lossless join. Why? Because by definition, there's a key on the right-hand side here, right? We take something where it says X determines Y, and we put X, Y together. We know that X determines X, so X determines XY, right? This decomposition always generates a thing with the key in the overlap between the original relation and the torn-off relation, right? So it's definitely lossless join. So that's good. All right. It's also, this is going to terminate. The argument is pretty simple. You're always making things smaller. You can only do this n times if you have n columns. Right? You run out of columns to tear off at some point. So that's great. So we can get a lossless join decomposition to BCNF always. And lossless join is our touchstone for correctness, so we can always get BCNF, and it's good. Here's a different example just to drive this home, okay? It's our contracts example, right? Contracts, suppliers, projects, departments, parts, quantities, and values. Projects and P is parts. Projects and parts. For a given project, for a given part, you can only have one contract. For a given supplier and department, you can only have one kind of part. And for a given project, you can only have one supplier. Okay, so let's start decomposing, because we didn't even need to understand that. SD determines P. We pull off SDP, right? And we pull we pull P out of the original. So SDP gets its own table. P gets pulled out of the original, so we're down to CSJDQV. To deal with J determines S, let's do that one next. We'll decompose the remainder, CSJDQV, into JS, and we'll pull the S out of that, and we get CJDQV. Okay? And actually, at this point, we have no more FDs to tear apart. We're done. And we have SDP, JS, and CJDQV. So that's an example of running this decomposition. Why did I bring this up? It seems pretty boring. The only real reason to bring this up is that you may have many different FDs that violate BCNF. The order you treat them, the order you play this game with them, actually leads to different outcomes. So you get different schemas depending on which things you decompose first. All right? So it's just something you need to know. The order of dealing with these could lead to different schemas. And for reasons of, say, not wanting to join things back together because you query them together a lot, you might want to worry about how it ends out for performance reasons. Okay? So just be aware. Now here's the bad news. We do get lossless join every time, but we do not. There is no theorem because it's false, or there's a counter theorem that says, it's by example, we'll see one in a minute, there may not be a dependency preserving decomposition for your schema. I'm sorry. So your schema may be a bad one where we can't get it into BCNF and have it be dependency preserving. All right, here's an example to prove this little theorem. CSZ, CS determines Z and Z determines C. You can't decompose this while preserving the first functional dependency. Just to go through it, CSZ is the original. CS determines Z, I get that right? And Z determines C. We can split it apart. The natural thing to do would be to tear this pair off into its own table. And we leave Z on both sides, but we take C out of one side. So we get these two tables, right? That's our decomposition. It's not dependency preserving. Note that I think this is all we're going to get that's non-trivial. CS determines Z and Z determines C. But how are we going to check CS determines Z? How are we going to check this guy? Because there's nothing transitive going on here other than C determining itself, right? CS determines Z, which determines C again. But we don't get any goodness across C and Z from transitivity of these guys. When we apply F+, there will be nothing useful that will guarantee this guy again. So it's not going to be dependency preserving. And to finish this proof, you really have to enumerate F+ and convince yourself that it's not dependency preserving, which is not that bad because this is a small f. Okay? So bummer. And we can look at these bigger things. You know, the one we looked at actually is not dependency preserving. It is lossless join. You can always do it lossless join, but it's not dependency preserving. Here's the funny thing. If you throw back an extra table at things, you can preserve the dependency in one place. So let's, rather than stare at that, we were sad that we couldn't preserve this guy. Well, this is kind of a crazy case, so maybe I shouldn't even do that. Here, we couldn't preserve JP determines C after the decomposition. So we'll just add a table, JPC. Okay? It's perfectly legal. It's extra. But it's the place where, without joining, we can check the dependencies. So you can take a FD here, JP determines C, and you can just create a table to check that dependency, JPC. Then you don't have to do joins anymore. It's also in BCNF still. Is it? I think it is. But it's weird because you have things stored in two places, right? These JPC tuples are stored in the JPC table, but they're also stored in some join between the other tables, right? And so you're going to have to be careful when you do updates to update in two places. In essence, you have an update anomaly risk. Right, so this is bad. But it's a way to enforce things without doing the join. All right. This badness, so I asserted that this is in BCNF. I think that's false, actually. Yes, question.
So you have to get rid of the Z and imply C.
So the reason I didn't do it in this example is when you create the auxiliary table, it's the same as the one we started with when you put them back together. So that's crazy. So that's a bad example. But if the original example just had one extra column for no particular reason, and it was here, okay, then this would make sense. We would add another table CSZ to enforce the functional dependency. All right, and it wouldn't be quite so crazy. So we would have this table, and that table. Yeah?
What's the difference between lossless join decomposition and dependency preserving decomposition?
So the question is, what's the difference between a lossless join decomposition and a dependency preserving decomposition? They're very different. All right? Let me emphasize the key thing, which is lossless join is about correctness. If your decomposition is not lossless join, it's lossy, then you lose information. You get extra tuples. So keep that very much in mind. Dependency preserving decompositions, which we just went over, are about whether you have to do joins to check dependencies. Right? It's just a performance question. We will check those dependencies and enforce them. It's just whether you have to do joins to do it. All right. So getting back to where we are in these dependency preserving decompositions, the remaining question is the addition of this extra table just to check the dependencies, is that a bad thing? It is clearly a bad thing. It introduces redundancy, right? You have CSZ triples here. Those same CSZ triples are represented in these two relations as well. This is our outcome, right? In essence, we added that. And we've got data replicated across these columns, okay? So that's bad. Is this collection actually even in BCNF? I have to scratch my head for a second. No, right? That's the whole point. We decomposed it because it was not going to be in BCNF. The thing we added back violates BCNF because of this functional dependency, right? So, bad news, all right? This is why you can't get it into BCNF. The whole point was you decompose it, okay, great, but it's not lossless join. I'm sorry, it's not dependency preserving. It is lossless join. It's not dependency preserving. You add this thing to make it dependency preserving because you can check it all in one table, but now it's not BCNF anymore, right? Because you got this functional dependency here that's not a key dependency. Okay, so this isn't going to be a good solution for things in BCNF. And in fact, this is the whole point of that theorem. You can't have your cake and eat it too. You can't have BCNF and guarantee that you will get a dependency preserving decomposition. Okay, big step back. We like BCNF. We sort of don't like to have to check dependencies with joins, but if we have to, we have to. Okay, that's one way to look at it. We like BCNF. Suppose somebody says to you, sorry, man, I don't want you checking dependencies with joins. Not allowed. It's too slow. Updates are happening in this database all the time. You're running around doing these joins on every update. That is not cool. Make this thing go faster. Well, the natural solution to that is what we just did, is you add back in this extra auxiliary table, all right, to check those things in one place, and it goes faster. All right, it goes faster. But now you have redundancy to manage, and you have to manage it carefully. This is the intuition behind what's called third normal form, all right? And you're not going to like it because it's a compromise. Somebody said to you, I know you want things in BCNF, but you're not allowed because it's too slow, and what we're going to come up with is something a little weird, and we're going to call it third normal form, and everybody's going to go, cool. All right? But if you stare at this thing too close, you're not going to like it. It's not going to make a great deal of sense. All right? It's kind of a hack. This is what third normal form is. We'll define a property. We'll call it third normal form, and it's going to be kind of a relaxed version. It's going to be like a mellow, everything's cool, man version of BCNF. It's going to be more relaxed. So we're going to say, just like in BCNF, something can be in 3NF if for all x determine A, either it's trivial, like we said in BCNF, or the left-hand side is a superkey, like we said in BCNF, or one other case, which we're going to be cool with too, because this is kind of like the co-op version. There's not a lot of rules. We're flexible about more stuff. So we'll also allow things where the right-hand side is like part of a key, It's like a column that's in some key. All right? It's called prime. We say A is prime if it is contained in a candidate key. That seems kind of weird. Let me make 2 points before we get going, or maybe at least 1 point before we get going. I want to join the third normal form co-op, okay? I want to get in there, and I'm really sloppy. So I'm going to say, hey, man, I got a table. It's got these columns, A, B, C, and D. I don't know, C determines D, okay? And I want to have a table where, actually, even better. Let's not do this. Here's our table. You can say A is a key. That's cool. And I want to have a partitioning of this table into like A, B, and C, D. And I want to convince you it's in third normal form. All right? Because I want to be cool. I want to be in a normal form. So I'm going to say to you, hey, I know that it's not in BCNF because what's wrong with this thing? What is wrong with this thing? Why is this not in BCNF? It's clearly an illegal decomposition. It's lossless join. It's lossy join, right? It's a lossy join decomposition. That's why it's bad. Forget it. Bad example. Let me give you a better example. That was just plain old bad. Well, I don't know how to make this example work. All right, let me just say what I'm trying to say. I thought I was going to get a clever example. I'm usually good at this. Damn. Bad teacher. The thing I'm trying to emphasize is the minimality of a candidate key in this definition. For something to be prime, it has to be on the right hand. It has the right hand side of the FD, like A determines B. For B to be prime, then there's some candidate key of this relation containing B, like maybe BC determines the whole relation. All right, then B is prime because it's part of a candidate key. But suppose you say, well, Z could be maybe prime because if BC is a key, then hey man, ZBC is a key too. So Z could be prime. Anything could be prime. No, because candidate keys are minimal, right? This thing is a candidate key. This thing can't be a candidate key because it's not minimal. So Z is an imposter. Z is not prime. Okay, this is my point. Took me a while to say that. The minimality in this definition is necessary. Otherwise, it doesn't make any sense. Everything could be part of a superkey, right? But not everything can be part of a candidate key. All right. If R is in BCNF, it satisfies the first two of these rules. And so it's clearly in 3NF. So BCNF, it has only two rules. It's the first two rules of 3NF. And anybody can get into the 3NF club if they can get into the BCNF club. Okay? So great. If R is in third normal form, though, there could be some redundancy, kind of like that. All right? And so this is sort of a compromise. And you use it when BCNF is not achievable. Like you can't find a decomposition you like because of dependency preservation or because the workload has some joins that you really want to keep the tables together. Okay? So you can always get into 3NF. That's the good news. The bad news is it's not exactly clear what it's enforcing because it's got some redundancy in it. So it's not that helpful. And year after year, I would try to teach this and justify it like I gave up. All right, 3NF is just like a hack. It's a little weird. All right. This is the difference between the two. It's that extra clause. The top one is BCNF. The bottom one is 3NF. The only difference is that 3NF is more relaxed. It'll accept things where the right-hand side is prime. Okay. We just said this first thing. We said all these things. I forgot to delete a slide. I put this into 2 slides for digestion purposes, but I left the original slide. I apologize. What do we get? Oh, we get some stuff. I can define some goodness we get, but it's just kind of definitions. So I'm going to skip this slide. All right, you're not responsible for this information. Basically, we're going to say, well, if it's not in BCNF, it's got either this problem or that problem. So I can say that much. And you're like, well, thanks. So we can break up the problems into 2 different kinds of problems. All right, but it's not clearly helpful to understand that. All right, so It's a compromise. How do we decompose things into 3NF? Kind of the way we did with BCNF, but we can stop earlier because, after all, we permit this crazy case in yellow, right? Where sometimes you get to the place where the crazy case in yellow is true, BCNF wouldn't be true, right? So BCNF would force us to deal with the thing that was in yellow and decompose further. So 3NF we can stop earlier than BCNF decomposing things. All right. And then this extra idea of if you want dependency preservation, you can throw in these pair relations. X determines Y. Cool. Add back XY, just like we did over here. All right. That may actually violate 3NF again, so you have to do this smart. And again, here, I'm tempted to just not teach you this. And in the interest of time, maybe I won't. So we're going to skip minimal covers and all that. The problem with doing it naively, if you add in the CSZ thing right in, you might get something that's not in 3NF again, and you'll just iterate, and you'll be in a loop. But if you do this in a careful way, you can prove that you can add in some extra things that will check the dependencies and will keep you in 3NF. And this is done using something called a minimal cover of the set of functional dependencies. And intuitively, and then I'm going to stop, the minimal cover is something that's equivalent to F. Its closure is the same as F's closure. It's a set of FDs that lead to the same consequences as your original FDs. But somehow it's as small as possible. All right? And the smallness is defined very carefully. But by having it be small as possible, you're then able to prove that the things you add back won't violate 3NF. And we'll just leave it at that. All right. So you will not be responsible for understanding why 3NF is good, nor will you be responsible for getting things into 3NF. Okay. But you will be responsible to know that it's something people do, and there's going to be a pull-down menu in your design tool someday where you're going to decompose my schema into what, and you'll be able to choose BCNF, 3NF, and you'll say 3NF. I remember that. Didn't make a lot of sense. I don't know what to do with it. It's like part of the history. I don't know why I don't get it. I actually asked my graduate professor at one point when I was teaching at Berkeley. I was like, dude, I got to teach 3NF tomorrow. What is it? He's like, I don't know. So maybe we need someone a generation older to bring back why they thought about it. But all right, you know it. We did it. We're done. BCNF makes sense. BCNF is like information theory. It's beautiful. You write down exactly what needs to get written down, nothing more. No redundancy. We're using functional dependencies to understand what we can derive from the base information, and we're writing down nothing more than that base information. Tuples, functional dependencies, and nothing redundant. So that's awesome. All right. Ensuring BCNF is a good thing to do. It will keep you from having anomalies. If you're not in BCNF, you should try to decompose into BCNF. But make sure that you preserve all your FDs along the way. All right? If it's not dependency preserving, it might be expensive to maintain. Right? But you can not always get a lossless join dependency preserving decomposition into BCNF. I'm sorry. Maybe then you use 3NF. I don't know. All right? Whatever you do that's not BCNF, you're going to have to be careful. There's going to be redundant data somewhere, either in the database schema using check constraints or in your application logic. Who's going to maintain that over time? Okay? Somewhere you're going to have to look out for this redundancy because otherwise you're going to get anomalies, right? You have been warned. All right, 3NF's not going to solve this for you. You're going to have to fix it somewhere else. Maybe you don't care so much. I don't know. All right, but you should fix it somewhere else. There are other normal forms. You can go past 3NF. There's 4NF and 5NF, and there's different kinds of dependencies you can define that actually are kind of interesting. This was a cottage industry for a while. BCNF's good enough. You know, you have the basics. If you really become like a database designer, you might want to invest a little more time into this area. All right, that is all I'm going to say about normalization and functional dependencies. I will point out, however, that functional dependencies crop up their cute little heads all over the place over time. So recently, one of my graduate students was trying to figure out how to determine, in a distributed computing environment, you're programming a distributed system. You want to figure out, could I possibly have a race condition with all this code running on all these machines? And if I do, what should I do about that? The checking whether you have a race condition had nothing to do with functional dependencies. One of the most efficient tricks for ensuring that the race condition would be taken care of was not to build a giant global lock, which is super duper slow, but instead to use functional dependencies to figure out exactly what data depended on exactly what upstream data and enforce this lock kind of data dependency by data dependency. So it was I was like, whoa, functional dependencies are back. They also come up when you're cleaning data. So you have data from this source and data from that source, and you put it together and it doesn't quite make sense, and you're trying to figure out how to make sense of the stuff that doesn't quite make sense. Functional dependencies to the rescue. It just keeps coming back in all these practical applications, even though it seems kind of abstruse. So you've heard about it here. Yes?
Does decomposition tend to exacerbate or help increase emissions?
Oh, jeez. Oh, boy. I'm not prepared to answer that question offhand. That's a very interesting question. You presuppose that you've already bought into my whole worldview that we should be programming with queries and distributed systems, and then you're asking me a hard question I haven't thought through. So let me think about that. Or maybe I'll have my graduate student think about it. But we'll get back to you. That's great. Great question. All right. By the way, I'm going to keep coming back to this over time. We have this language called Bloom, which is a general-purpose distributed systems programming language that's all queries all the time. It's super cool. You should check it out. It's at bloomlang.org. It's an interesting language, and also you can prove a whole bunch of stuff about programs written in it. It's great. Side note. We have a few minutes left, and I want to tee up an idea that you're going to do in your homework 4. Okay? And we might want to revisit this next time, but in the few minutes we have left, let me tee up this idea. Remember how we said last time, what's the difference between a function and a relation? Remember that? This has everything to do with Bloom, by the way. What's the difference between a function and a relation? Well, a relation is a table with 2 columns, let's say, a binary relation, x and y. And you can put anything you want into it. A function is also a table with 2 columns, x and y, all right, except that x determines y. That's a function. All right? Gee, really? Yeah. Remember we said cosine. That's nothing more than a table where x determines y, and you guys reminded me that the cosine of 0 is 1. Okay, thank you. So that's one entry in the table, and I bet the cosine of 180 is not 1. It's probably 0. Am I remembering that right? Or did I get that wrong too? It's minus 1. See? And my daughter's about to learn this stuff, right? And I'm going to have to, it's minus 1? Yeah, that makes sense, right? Yeah, okay. Yeah, 90. Good, thank you. 90 is 0, and 270 is 0 again, right? Am I right? All right, we're done, right? No, unfortunately, that's not how cosine on the calculator works. It has more entries. It's a really big table. It's infinitely big. It's defined over the reals. But it's just a table. It's just a logical table. Let's take that idea and run with it. Suppose I have a big bag of numbers, and I want to compute their cosines. So I got a whole terabyte of numbers, call them n, and I want to compute cosine of that column. All right? One way I could write that down is I could say, well, here's my query language. I'll write down select cosine of n from t. Right? That's what Postgres would do. What the heck is that? That's not relational algebra? No. That's not good. I'm a purist. All right? No, I want to write this as select. What was it? We're going to call it c dot y from, you know where this is going, t comma cos c, where t dot n equals c dot x. I want to join this table with this table. That's how you do functions, man. None of this weird keywords no one's ever heard of. Write it down. You got a function, write it down. Right? Oops, that function's infinitely big. That table's infinitely big. Why would I even, this is perverse, right? Like, why think about the world this way? Here's a good reason. Because cosine isn't something your computer knows how to compute. Let's take a different example. Instead of cosine, suppose what I want to look up is top-ranked Google hit for whatever I'm doing. So there could have been select top-ranked Google hit of n from t. There's a bunch now of words. All right? If I run this query, you know what Postgres is going to do with this function? Top-ranked Google hit. It's going to get a tuple. It's going to make a REST call to Google, and it's going to wait for the answer. And then it's going to get the answer. It's going to get another tuple. It's going to make a REST call to Google. And it's going to get the answer, right? That is the wrong way to think about function invocation in an environment where data is super big and far away. Function invocation is a terrible way to think about things. Join is a wonderful way to think about things, right? Because as answers come back from Google, they can be joined with new T's. Suppose that you have 2 copies of the same value here. After you get one of them back from Google, you can join it with the other one instantly, right? Join is really asynchronous batch REST calls. This is insane, right? No, actually, this is the right way to do things. It's just that we're forced to program it in JavaScript with crazy events and callbacks and closures and stuff. It's just an asynchronous join. So homework 4, you're going to implement this, right, in Spark. So you're going to have a big data system making cloud invocations of service calls. It's like all the cool things all at once, right? And it's all going to be done through joins. And that's enough for today.